Okay, welcome back, SL2. A few more vocabulary words before we see how this is going to apply to our functions. So the first thing is to realize that we have relative max and mins. And these relative maximum and minimums, again, are going to be the points where the function is turning. It's a turning point. And if you look around that section, it would be a maximum relative to this area. It's not an absolute. It wouldn't be the biggest maximum of the function, but it would be compared to the things around them, it is a maximum. And the same thing here with our minimum. If you compare with the x values around it, it would be a relative minimum. So then if we think about what we saw in the Geo Sketchpad activity here, this graph, if you think about how on our maximum, our slope of our tangent line here was positive when it was increasing and then negative when it was decreasing. We can then recreate that on our just as a knowledge point for us. So this is part of our definition of our relative maximum. You can draw a little graph here with a maximum and then realize that our first derivative on this, the left side of our a value, for a is the point of x where it's at our maximum, then that value of the derivative would always be positive because of our slope of our tangent for the increasing section would always be a positive. And then at a would be 0. And then going down here, or decreasing, that slope of our tangent would be negative. So this is called a sign diagram, and we're going to practice those in a few minutes. But this is one of our definitions. For the relative local minimum, as you would guess, it would be in reverse. For our minimum, this section would be decreasing, so our derivative here would be negative. And then this section here, our derivative of this point, our slope of our tangent line would always be positive. So here's our sign diagram. And then B again is just our x value at that minimum point. Okay. Another time when we could have a slope of 0 would be called a point of inflection. And let's go ahead and graph one of those. And so you can kind of see what it looks like. A point of inflection occurs on a graph. And you can see that at this point here, there would be a derivative of 0. So that would be our point of inflection, where we would have a derivative of 0, but no change in direction. Okay, and if you think about what our sign diagram would be for a point of inflection, is it would stay the same, because this, and for this graph, on this side of our point here would be positive, and on this side would be positive. So for this graph, our sign diagram, and let's call that point, it's almost at 0. Let's just call that C there. So our sign diagram on both sides, because our slope of our tangent is always increasing, would be positive. Think for a minute, what would it look like if it was a decreasing? What would be our sign diagram at a point of inflection? So at this point right here, our sign diagram on this side of our point, again we'll call that C, and well, let's call this one D. At this section here would be negative, and here would be negative. So you can see when you uncover this, we're going to have, if it's a point of inflection, our sign diagram would look like this, depending on which kind of point of inflection. If it's for a increasing function or if it's for a decreasing function. And our last vocabulary word is a critical and stationary point. These is a point when the derivative is equal to 0. So these would include a critical or stationary point would include a relative maximum or a relative minimum and also a point of inflection. So that would include, see if we can have more space here, includes a local, and again a local is just another word, a local max for relative, a local max, a local min, plus our point of inflection. Okay, one last part with our vocabulary. Want to bring back some notation for intervals. The first part here is a definition for an interval of real numbers, and the derivative is defined for all x in S. Then when our function is increasing on S, if and only if our every element in S, the derivative is greater than 0. And then the opposite would be the case when our function is decreasing on S, if and only if for every element our derivative would be less than or equal to 0. So this notation you'll see, and it's the same thing we've been talking about. Last, I wanted to show you, just remember back for inequalities, what x is greater than or equal to 0 means, and then if we had an interval where the x values would be less than or equal to 5 or greater than or equal to -2, remember in Algebra 2 we would write it like this with our brackets because it includes those points, -2, and then would be all the values between -2 and 5 and would include 5, and that's why there's a bracket here. The IB way is the same. You'll see it written the same way, but you'll notice it's going to be written a little different here when it doesn't include those points. So if you have an x between less than 5 and greater than -2, and it doesn't include -2, so it'd be only every value greater than -2, then when Algebra 2 we would write the parentheses here because it doesn't include those points. And IB, you'll see it written in reverse. Those brackets will go out to show that it doesn't include. So just wanted to show you that notation. Okay, so a couple problems here to practice. We're going to be given functions. We'll have to graph them and find these critical points. So let's first, this question just asks, when is the function increasing or decreasing? So our first step is just finding those critical points. So remember, our first step would be finding the derivative and setting equal to 0. So let's go ahead and do that. We'll set our derivative equal to 0. First find our derivative and then we'll set equal to 0. So for this function, our derivative would be -3x squared plus 6x. Okay? So we want to know where those critical points. Where is that slope of the tangent line 0? So we will set our derivative equal to 0. Okay? And the fastest way to find where this is equal to 0 for me with this problem would be to go ahead and factor. And I'll look for my greatest common factor of -3x. And I'll realize that inside here we'll have an x minus 2. Okay, and then I'll use my zero product property to set both my factors equal to 0. and x would be 0 would be one of my critical points, and x equals 2 is my other. And now we're going to just set up our sign diagram. We want to find out where my function is increasing or decreasing. And this, we know there is a change at these points. So that will be our points where we'll be uncovering what happens there. Okay, so we'll have a couple different sections here. We'll start off with what's left of my x equals 0 here, and that would be negative infinity would be my first section to think about. And then in between here, the different thing might be going on. We're not sure yet, but between 0 and 2. We know at 0 that the derivative is 0, but so this section, these two sections we'll be finding out. And then again, the derivative is 0 at 2, so we'll see what's happening at 2 and all the way to infinity. And there's no other critical points, so those are the only ones I need to look at. Okay, so now I'm going to just take the derivative and plug in different values in these intervals. So for this interval, the easiest one that I might plug in might be -1 into my derivative. So I'm going to go ahead and do that over here in on the side, because in my sign diagram I'm just going to put the sign. And so if I plug in -1 here to my derivative, I will get a value that is negative here. I'll get a -9. If I plug in any other as well, I'll end up with a negative here. So here I can tell my function is decreasing. Let's plug in a value into the derivative in between 0 and 2. So in this case, I'll plug in 1 again. That's a pretty easy number to plug in. And I will get -3 plus 6, and that's a positive value. So I know here my function is increasing. And then in my last section here, let's plug in a 3. Okay, and here we're actually going to get a negative if we finish that out. That's clearly going to be a negative number. So here we'll see that our function is decreasing because our slope is negative. And then at that point there, 0, it's going to increase again. And then here at our 2, it'll be 0 again. And then it will decrease again. So we can make that a little prettier. Let me stop and make that. Okay, so you get the gist. This is just a sketch. Here's our negative. It's in this section, the function will be decreasing. Here, the function would be increasing. And here, it will be decreasing again. So we will answer those questions with the interval. With this section would be decreasing, and that would be decreasing, and this one would be increasing. Let's see how this works for a stationary point. So we know that anytime we see the horizontal point of inflection, there shouldn't be a change. So just take a look at this and realize on our first derivative is going to be equal to 0 again. And let's look at an example of y equals x cubed. Okay, if we take the first derivative, the dy dx, we get 3x squared. Okay, I'm going to have you pause the video and just try this, find those points, and then I'll bring you back. Okay, so you should have found there was only one critical point. When you set that equal to 0, you can only get one, and that would be at the value of 0. Here we have two sections, negative infinity to 0, and when you plug in the derivative, you get positive, and the same here on positive. So that's a horizontal point of inflection.